So, welcome everyone. Welcome to my speech, Taking Your Side Effects Aside. So let me tell you a few things about myself. So my name is Tomasz Kogut. Like it was said, I'm from Warsaw. I work for Adform as a software engineer in something called tactical research, whatever that is. I've been doing Scala since about 2011. If you want to catch me after the conference, here's my internet handle. Using this opportunity, I would also want to tell you about a Slack group we have called Scala Poland. So if you want to hang out with people who like to talk about Scala, computer science, etc., just Google Scala Poland Slack and register there. Okay, enough about me. So who I end this talk to? So as you probably already know, Scala community is quite wide, right? So there are some people who are more to the left, treating Scala as a better Java. There are people who treat Scala as a handicapped Haskell. So side effects are actually something that is a concern for all of us. So side effects are the thing that actually blows your application on production. Side effects are the thing that causes your application to behave in a ways you wouldn't even imagine. So we all need to watch out for those. So now let's look how to spot a side effect by doing something that probably all of you have done, by brewing a tea. So to make this delicious cup of beverage, you need three things. You need tea leaves, you need a cup, preferably a clean one, and an electric kettle for boiling the water. Some might say you might need milk, but let's leave that off. Well, we're not at the conference about brewing tea, right? So we have to somehow put that into some pseudocode. So how would that look like in a pseudocode? So we have some function f, we put all the ingredients inside, and you expect to get the tea back, right? That's pretty obvious, and that's how you would probably implement that. If you look closer, those two first arguments are actually a bit different than the third one. So they are more static than the third one. So if you leave a cup and the tea leaves on the table for 10 minutes and get back, they're as good as they were 10 minutes ago, right? If you leave the kettle on the table for 10 minutes, well, the water might have cooled down, but that might be at the least of your problems because like kettle might get broken in the meantime. So for example, I don't know, maybe you have a cat and in that 10 minutes the cat has bitten through the cable. So the kettle is not operating at all, so you cannot make the tea. You might have a problem somewhere deeper. So the kettle is fine, but you have a dependency on an external service, a power plant, and that external dependency is not working, so it renders your kettle like it wouldn't work at all. So actually how I would expect that code for brewing the tea to look like in Scala code, and this is something we see a lot. It's actually people tend to put those things that are like dynamic into futures. You need to put a kettle in the future because like it needs to boil the water. It can break, so it can throw exceptions, right? And then you would probably take the future and map it to some function, and then you would have not a tea, but a future of tea, right? And of course, you would probably have this execution context all over your place, right? So this is a lot of Scala code you can actually find. So people tend to start with something that returns future, and they tend to put it everywhere. So this pollutes the signatures a lot. So like looking at those three things, you can see that we have arguments that are more like data-like, static, lazy, or also we have things like that are more service-like, dynamic, or eager in it operating. So how can we fix that? So you can tell that if you have a function that is impure, so it actually does some side effecting, so you can split it into two parts. One that does the side effecting thing that you need, and one that is like not doing the side effecting, only has the needed transformations. So how would we do that? So actually we're not interested in the kettle, we're interested in a boiling water, right? So we would just change the signature of this function to something like this. Actually, look, now we don't care from where the water comes. Maybe your neighbor brought it for you. This also helps with testing. You don't need to actually now depend on a service. You don't need to work with the futures and stuff. You just want to work with the data. Your business logic is mostly in the data. So how to spot those kettles in the wild? So there are different types of those kettles. Those are your databases, RPC systems, like when you're doing REST calls, even when you're doing print lining. Actually, this is something that is not repeatable, right? This changes with time. So yeah, so look for things that actually can change with time and try to depend on things that are more data-like. So I need to get back to why not future? Why we don't want that future to be in that code? So aside from the thing that I said, that we're polluting the namespace with implicit execution context everywhere, the problem with future is that it's eager. In the moment you create a future, it's already running, and you can do anything about it. So it already can be side effecting somewhere. Somewhere deep inside your program, it may, I don't know, throw exceptions, call databases, call RPC systems, whatever. So what we actually want to have is we want to have a pure core of functions, data structures, that are actually static. And we have this gloomy, dark place where all the side effecting happens. And well, we know that we need to have these side effects, but we want to control them. It's not like side effects are bad per se. Side effects are the thing that actually keeps your application do stuff, but you want to control them. You want to actually have a place when you say, now, do the side effecting, because I'm controlling you. So what we want our programs to look like is they want to be composed of things like best, functions from A to B. This is the simplest case. You don't need to then think about almost anything, right? And the second thing is functions from A to F, B. Why we need those functions? Well, because the world is a messy place, right? It's not like you're calling RPC system and it will just respond. It can respond with error code, right? It can, the connection might not work at all, so it might be an exception. So the F here can be try, either, whatever option. And as I said, future might not be the best fit always. Sometimes it is. But what we're going to do in the next part of the presentation is we're going to actually create a new type that will shield you from the side effecting that we've talked about in the previous slides. Okay, so now we're going to go through some slides that will tell us how to create this type. So this type is historically called I/O. The name comes from Haskell. It's actually called differently in Scala. We'll get to that, but I will just call it I/O because it's convenient. Okay, so let's try to implement this type I/O that will shield us from side effecting. So we'll start simple. So we have a trade I/O. So that trade has one method that does not return, well, it returns units, so it's returns nothing. That method run will actually be the method that will call the side effecting. So we want to have this I/O type that will contain the side effects, and at the place we want them to run, we'll call the run method, right? So how can that work? Let's implement some, like, this is like something that you would probably need. You want to print things on the console, right? So you have a function that creates an I/O object by doing new I/O, and we just bind the print line into the run method. So now if you call print line with some string, it won't print anything, right? Until you call run. Of course, you can make it as complicated as you want. You can put some branching or stuff like that. So what is actually interesting in this is that you'll probably have a lot of I/Os in your code, because you have a lot of side effects. What you probably heard a lot is that programming is all about composing things, right? Especially functional programming, that you want to compose things. So now we want to compose I/Os with each other. So let's add another useful method. Let's call it and then. And then what we'll do, it will take two I/Os and it will sequence them. So it will run one after another. So first it will run the outer I/O, then it will run the inner I/O, right? Okay, so let's do some. Let's go to some example. So here is the created before print line with the word hello. We sequence it with and then print line goodbye. So we have an object polite of type IO. It's a single object. We call run, and it says hello goodbye. Okay, that's all good. Now the thing when it starts to be interesting is that what we did here is we actually moved from running code to having a data structure, and data structures can be kept in other data structures. So here's another example. We have a list of cities, Warsaw, Krakow, Wrocław, and that list of cities we map to the printline function. So now we have a list of IO objects, but a list of IO objects is not such a convenient thing to have. So what we do is we reduce it to a single IO using the fold left method on the list, and then combinator on IO. So then we have one single print all cities object of type IO, and then we call run, and it invokes all the side effecting that we want. So what we done here is we shifted our concerns from, like, we have code that is now data, and that is actually a good thing. As I said before, like, we saw that the tea leaves and the cup was actually something that didn't make us any trouble. So now, the things that did us some trouble, now they shouldn't, or at least to some point where we'll call the run method. Okay, so we saw how to write things, right? We had a print line. We also need to read things to actually do anything useful. So what about input? So we need to change the IO type a bit. So we'll add a generic parameter A that will be returned from the method run. What I can tell you is if you see something like this, that you have a tray that is parameterized on some generic type, there's a good chance you can make some usefulness from these two methods. You probably know them very well. So now our IO can be used inside for comprehensions. So the implementation for map and flat map is actually fairly simple. So we just create in both ways the new IO object and just run the outer IO and just pass it to function. And in the flat map, we also do the same, but run it again. So an example, how to do readlining. So we also create new IO. This time it's parameterized with string, but with string is what we'll get from it, from calling run. And we call the readline method from Scala standard library. Or is it Java library? Okay, and here we have this readline thing that we defined before. We have a print line thing. And here is how you can create a bigger programs out of it. Because we added flat map and map, we can use the for comprehension. And now we have an enter number program that's of type IO unit, because yield is returning unit. What we do, so we print line, enter a number, then we read line, map it to an int, and we then print this number on the console. So let's run this program. So it asks it for a number, we insert the number and print it out. Okay. Like, here's another cute program. So this is how you do hello, echo with this style. So you do a read line, flat map, print line. And when you try to run it, it goes like, insert something, it will print it something. Okay, so what we achieved here is we're now in the control of the side effects. So this simple IO type that we've built, it's already controlling all the side effects we can have in our program. So we know how to read data, we know how to write data. So are we done? Well, almost. The IO has a certain flow. So let's break the IO, and let's try to think of a use case where this won't work. So think of a case when you would have an IO object that you want to loop like forever. So you want to put an IO object inside that function forever, and you want it to just do that side effecting all the time. So how we can achieve that? So we're calling in recursively the method forever on that IO again, but we assign it to a lazy val, so it doesn't run yet. And then we chain it with the same IO, right? So what we have is we have an IO and another IO that is lazily invoked later. Okay, so let's try to use this. So we have a forever print line, hello. So we have a val greet like mad that should probably print hello forever, right? Do you know what will happen when I call run? Exactly. So this will Stack Overflow. So we'll see a few of those hellos at the beginning. Well, actually a lot of them because the stack is pretty deep. And at some point you'll have the Stack Overflow error. And what is pretty sad is that Stack Overflow is actually a fatal error, so it will tear down your virtual machine. So, well, we need to do something about it. By the way, do you know how Future does it, that it doesn't overflow? Have you ever wondered why? So Future does not overflow because he got this second parameter, the execution context. So every time you do a flat map, you're actually crossing the asynchronous boundary. You're submitting a new enable to the execution context. So that's why you get a new stack. Every time you get a new stack. And this works. This might be a good thing or a bad thing. It depends on your use case. But well, the Future won't Stack Overflow. So where is the problem in our code? So here it is. It's actually just recursively running ourselves and eating up the stack one by one, right? With every call. With every flat map, we're eating up some stack. So, well, we need to do something about it, right? So let's keep to this maxim. So code is data. Yesterday, John said something about AKA do nothing, right, rule. So yeah, let's redo this thing, and let's do nothing. So instead of calling functions, because like calling functions created the problem in the first place, right? So let's just do nothing. Let's just create new data structures. So instead of actually calling anything on flatmap, let's just create a new data constructor called flatmap. Why not? This data constructor will take the outer IO on the first argument and the transformation on the second. So what now the flatmap will do? Well, it will create a new data structure and like it doesn't execute anything yet, right? Okay, so let's go with the map. So we want to be lazy again. So what we can look at it. So we got this f from A to B. Well, if we could change that f from A to B in IO context, then we could use flatmap, right? So we need to have a way to change this f. So let's add another data type. So this data type will allow us to just hold some constant value. And now implementation of map is pretty simple. So we take this f and we lift the result of f from B to I of B. Okay, so we did something. We don't know yet why, but let's try to keep on doing. Maybe we'll come to a place that it actually works out. So let's try to do the print line thing using the new redundant data structure. So print line, maybe this, but no, this is not the right way to do it. Why? Because we're doing the same, like not mistake, but this is the same like what Future does. It will eagerly evaluate the print line, and this is not what we want. We need to think of something else. So let's add another data type, suspend. So we want to suspend the computation. And now our print line looks like this. So now let's get back to the forever call. So how does it look now? So the IO forever call is actually a flat map, right? So now, if we call IO forever on the suspended print line, we'll get a flat map, an IO here, and a recursively data structure build, like that will build up forever at will. So this is very similar if you remember streams, the Scala streams, you have a head and a lazy tail. So this is something very similar. You have a lazy computation at the beginning and a lazy computation in the tail. Okay, so this was said like a few times already, but there comes a moment when the data has to run somewhere. So so we need the run method. Okay, so how can we write the run method? So we know that I/O is actually a seed trait with case classes beneath. So let's do what most programmers will do. Let's pattern match. So the first case is actually pretty simple. So if we have a return, so we have the value in hand, so we can just return it. If we have the case of suspend, so it's only a function call OA. So again, we call the function and we have the value. And now comes the tricky part. So we have a flat map. So flat map looks like this, like at the bottom you can see it. So what is y here? So y, like maybe we can just go and try to avoid. Maybe you can also here run functions, maybe it will work. So we could try to write a naive implementation like this. We can run the y, then pass it the result to G, and then run everything. But well, we already tried this. So this can also stack overflow. So to avoid this, we would like to have a tail recursive call, right? But this is not a call in a tail recursive position. So no, this won't work. So let's try to do the same as we already did. Let's try to pattern match on the first thing. So the first two cases are actually very similar to the things that we already did before, right? So there is nothing to actually think much about. The flat map thing is very tricky. Why? Because the y1 can be again a flat map, so we could again pattern match on it, right? But we don't know how deep is it. So so this becomes a bit problematic. So let's try to, like, again, write implementation from what we have. So we could do something like this. We can flat map y1 with g1 and then flat map it with g. But if you try to run this, unfortunately, this is, again, a flat map inside a flat map. So we came from flat map inside a flat map and created the same thing. So we will be looping. So this won't work. And now comes I think, a very funny moment because, well, the monad loss comes to the rescue. So it actually turns out that monad laws are not only to oppress you, but they actually can help you with something. So there's this monad law called associativity, that if you have three things that you're composing, you can compose the first two and then the third one, or you can compose the two third together and then compose it with the first one. And we can do exactly this here, and it will automatically rewrite our expression. So here's the original run method, and here's the shifted to the right. So now the composition actually happens on the second and the third argument. And here is what will be built beneath. Again, a lazy data structure. So it will rewrite the whole expression right-wise until it will hit the bottom type like return or suspend, where there's a value. So this will actually work. And this is the answer to the Stack Overflow problem. And this is actually something that is very common. This is called trampolining. And what we do here is we're trading stack for heap. So instead of doing calls, we're creating data structures. And when we call that data structure, it returns the control back to us. So it builds a call tree, let's call it like that. Of course, everything has a cost, so this is not for free, because like calling functions directly is of course cheaper. And already a lot of people spoke about free monads, so if you know what it is, trampolining is actually a specialized free monad, so IO type can be written as a free monad over unit to A. Okay, so So we got our IO type. It actually seems to work. So one more thing we need, well, we need more things, but one more thing that I want to go with is we got a lot of asynchronous APIs. So we want to add asynchronous computations. So let's create this asynchronous possibility for our IO type to work with it. And the implementation will be pretty dirty, but the good thing is if you use our IO, you don't need to actually use these dirty things. You don't need to see it. They are like implementation detail. Okay, so how do you think we'll approach this problem? Again, code is data, so let's just create another data type. So let's create a data type called async, and it will hold, what it will hold actually? It will hold something that does asynchronous computations, and this is data. And what signature does the asynchronous computation has? So I know this is not actually easy. I remember like seeing it for the first time and it's like glazing into it for half an hour to understand it. But actually, this is the signature of asynchronous computation. So it's easier to actually look at it this way. It's look at on the register as a method that has a callback on the argument. So because what is asynchronous computation? It's like do some work, and when you're done, here's a callback. Use this callback, and using this callback, the result will get back to me. So this is exactly what we're doing here. So the register body is the work, and at the end of that work, call my callback, and the result will return to me. So here's an example. So we have a double on separate thread method. So we take in a double. We execute it on a global context. And as you can see, the undone is actually this callback. So the work doubling by 2.0 is done, and then the undone method is called to return it to us. And here's a sample program. We read line, map it to double, flat map it. Then it will actually compute it on a separate thread. Again, we call flat map to print it. At the end, we can call run, and we're done. So we need to extend our run method. So this is the dirty part. So actually, we need to. We're doing a monadic composition, so we need to wait for this result. We need to just on a JVM, you can do it like this. You can create a countdown latch. You can create a local placeholder for the value, and in the register function. This is the callback. This is the undone from the previous slide. So when you're done, just pass this value to me. I will just assign it to my local placeholder, and I will release the latch, and I will go on with my life, right? And return A at the end. So as I said, this is pretty ugly, but if you use the I/O, you don't need to look at it, and that's a good thing. Actually, a lot of things in Scala done in FP way are really ugly beneath, but the API is beautiful. A wrap up. So I/O is actually called a task. So there are at least 2 implementations out there in the wild, 2 libraries you can use. So one is called Monix. The second one is called Functional Streams for Scala 2. As I said, you just probably should use it where you use future, but now the task is lazy, so you can say where you want your side effects to happen. If you're more on the reactive side, you're already using akka and things like that, then probably Monix is a better choice, because if you call run on a task from Monix, it will return you a future. So it should play nice with all the methods you have already written in your projects. If you're using libraries like HTTP4S or Doobie or something, then you're already using tasks, so I don't need to tell you that it's useful. Monix and functional streams for Scala 2 also have streaming I/O, because our I/O type cannot express streaming, but those 2 libraries has it. Well, our IO type is actually, like we didn't do a lot of things, like for example, error handling, right? But this was just a showcase. So I will put this slide somewhere on the internet. So here are some of the readings, watchings you can actually do if you're interested in it. And my time's up, so thank you for listening.